Oh, there you go, on sustainable product metallurgy. And we have 3 speakers for you this afternoon. We have Peng Gong, Mark Rainforth, and Matt Green, we're just talking to over lunch. And generally speaking, the theme is about engineering steels, but also hydrogen, and Peng is also thinking about fusion reactor steels. So without further ado, I'll hand over to Peng, who is now a lecturer, congratulations, in the University of Manchester. So
Thank you so much, David. Okay. Good afternoon. My name is Peng Gong, and I will give a presentation about a novel multi-scale microstructure design to address the strength ductility trade-off in reduced activation ferrite martensite steels for fusion reactor. And the presentation contains 3 sections. Firstly, I will quickly introduce the steel making manufacturing process and why we need to developing green steel technology. And the second section, we will discuss the importance of renewable energy in green steel making and how the steel industry can support the renewable energy with a case study to use the role of steel in fusion reactors. And firstly, let's give a short introduction of steel making process and explain why we need a green steel technology. There are 2 conventional steel making process. One is, as we know, is a blast furnace route, and the second is direct reduction route. And both 2 routes requires the iron ore, which is reduced to pig iron and emitting carbon dioxide, and by adding the coal. And there are nearly 17% of the carbon emission in steel making is generated in the pig iron process. And as it reports, the steel industry is responsible for around 2.6 billion metric tons of carbon emission, and which account to 8% of global carbon emissions. However, the steel is a fundamental key materials in global economy and modern civilization, which is for mobility, damage tolerance, strength and ductility, make steel as an ideal material for construction, manufacturing, engineering applications. Therefore, the production of steels increased by time, and however, recently published the low carbon roadmap requires us to reduce the carbon emission, and by 2050 should achieve net zero carbon emission, which requires the steel industry to reduce nearly 90% of carbon emission. There are 2 main methods that we can reduce carbon. Firstly, we can use the natural gas or hydrogen to instead of coal in the iron core reduction and only emission water with the spongy iron. And the second method, we can use the arc furnace. And this route, we can use nearly 100 steel scrap, which we can reduce nearly 80% of carbon emission. However, as we already reported that this route requires the large amount of electricity. And if we can use the renewable energy, as we discussed, to produce electricity, and this will help us to achieve the full green steel making without carbon emission. And I list out a few renewable energies, for example, the fusion reactor, wind, solar, etc. And my next section, I will discuss how the steel industry can contribute the renewable energy. Previously, we know that the renewable energy important on steel making to supply the electricity. And that's the steel company important for the renewable energy. I will use the fusion reactor to give an explanation. So why we choose the fusion but not the fission? This is because fusion can produce 4 times higher energy compared to fission with less radioactive waste. And as well as the interaction of fusion only requires the deuterium and tritium, which are the abundant source compared to fission, and as well as there is no nuclear disaster. So UK announced to build its own fusion reactor and aim to driving the electricity power by 2040. And to build the fusion, we face the challenge because the fusion requires the harsh surface environment, especially challenge the materials design because compared to fission requires the wider range of surface temperature from the 1000 degree to 300 compared to fission, and as well as has extremely high displacement damage. And this will especially challenge the forced wall and the blockade, because the forced wall and the blockade are the materials directly face the irradiation, plasma, and extremely high temperature, and protect the external components. So currently, we have a few materials we can select to be the forced wall and the blockade material. To compare with other materials I list here, the reduced activation ferromagnetite steels with its high thermal conductivity, low thermal expansion coefficient, radiation resistance walling, and helium's brittlement, as well as important, they have the commercial scale manufacturing production chain to supply the productions in the future, which let the IFM steel become the ideal candidate to be the forced wall and the blockade material. But we still have the challenge to select IFM steel because they have a narrow operation window. This is due to the low temperature hardening induced by the irradiation and the high temperature embrittlement. At a surface at high temperature, most of the precipitates will be dissolved and the steel will lose strength, and as well as the irradiation will induce the voids and defects on the grain boundaries and increase the embrittlement. So currently, the surface temperature for IFM steels between 350 to 550. And the current research trying to solve the issues and open the operation window, but they are mainly focused on 2 areas. One is design the high temperature stable precipitates. This can increase the steel strength, and also the precipitates can become the trapping position for the irradiation-induced defects. And as well as the second option is to produce a full martensite structure. And this structure can avoid the ferrite phase abnormal grain growth and improve the steel strength. But we solved the high temperature irradiation-induced embrittlement. But the issue is we also increase the strength, which will increase the irradiation-induced hardening temperature to nearly 500. So that's give us a question: how we can open the operation window not only for the high temperature but also for the low temperature. In my concept on steel design, I will produce the nanoscale subcell structures in martensite. And this structure will improve the ductility, which will benefit for the low temperature hardening temperature. And as well as I will keep the same concept to produce high temperature stable precipitates, but I will maximum the number density and refine the precipitate size, so we can maximum the trapping effect, which the defects and voids induced from the irradiation. And as well as importantly, I will achieve the nanoscale grains on the interface grain boundaries, as we know that the irradiation will induce the voids and the defects on the grain boundary, which lowers the strength and increase the brittlement. So if we can produce the nano grains on the dual phase grain boundary, on the interface grain boundary, which we're trying to avoid the voids coalescence and interconnect to failure. To achieve the desired microstructure, I modified the manufacturing process. Firstly, I increased the rolling temperature on the stage 1, which achieved the partial recrystallization. And second, I reduced the stage 2 rolling temperature to near the phase transformation temperature, which achieved the strain-induced ferrite. And I also added the warmer rolling. This rolling procedure can produce extremely high dislocation density. And after the standard heat treatment on the rolled steels, we achieved the extremely high strength and combine the excellent elongation ductility to compare with other standard IFM steels. This is our work. We combined the ductility and the strength. The ductility increase did not lose the strengthening. And as well as the important that the stage 3 steel obtained the post-elongation properties compared to the standard IFM, compared to standard Eurofoil 97 IMFM steels. And we analyzed the microstructure to give the mechanism explanation why we can achieve both ductility, excellent ductility and strength. From the image showing above is obtained from the current, the newly designed steels, and the bottom images from the EBSD and the TEM prepared from the current Eurofoil 97 steels. We can find that we achieved the bimodal structures, which we have larger ferrite grain size, and also we achieved the nanoscale grains in martensite phase. This is a typical martensite. And the bimodal structures improved the ductility, but no consume the strength. And as well as, importantly, we have the extremely high dislocation density in ferrite phase. And those dislocations become the precipitation position, which maximum precipitates number density. And we calculate the yield strength contributed by grain boundaries, dislocations, and the precipitates. From the results, we can find that the precipitates contribute half of the strength, which means that the strength improved by the precipitates, and the ductility improved mainly because we achieved bimodal structures. And we also analyzed the type of the precipitates through the EDIs and diffraction. And this nanoscale precipitates in ferrite phase are mainly the titanium vanadium carbides. And the small angle neuron scanting technique also used in this study. And we analyzed the standard Euro4 steels and compared with our newly designed IFM steels. What we found that the newly designed steel achieved 0.16% of the precipitate, and this we cannot find in the Euro4 97 steel. And we also prepared a sample from the tensile fracture surface, and the specimen found that we have the nanograins on the dual phase grain boundaries, and this is a TEM image. We found that we have the nanograin on the dual phase on the interface grain boundaries, and besides the nanograins, we have the voice structure on the dual phase grains, and this structure illustrates that the nanograin provide the voice connected to the interconnection to failure, and which we obtained the excellent post-elongation property characters. And this character important for the irradiation steels, because under irradiation we will induce the voids and defects on the grain boundary, which will cause to failure, and the nanograins can delay the failure occurred. And to conclusion of my research, I list out here, and we can the steel industry can continually produce the excellent mechanical property steels to further contribute the renewable energy and accelerating the UK's goal to achieve the fusion reactor by 2040. And that's all of my presentation.
Right, unexpected. So now for something completely different, the role of hydrogen in steel. So it's got my name on it, but of course it wasn't me that did the work, it is these lovely people here, particularly Peng, who has just spoken to you, so this is mostly her work that I'm talking about. So hydrogen brittlement's been a problem for a very long time. It's been recognised for over a century, and despite all that time and intense research into it, we still don't fully understand it. What we do know is that a lot of failures from hydrogen embrittlement, and that those failures tend to go up the greater the strength of the steel. As we move towards a hydrogen economy, we're going to be transporting hydrogen, and that's largely going to be through steel pipes. And so what the hydrogen does within that steel is also going to be of interest. Hydrogen is a very difficult subject because we can't see it. But we know roughly where it goes into the lattice. So here we have a microstructure, and it goes in all sorts of places. So the hydrogen can go into vacancies within the lattice. It quite likes it there. It goes into the grain boundaries, into voids, dislocations particularly, lattice defects, precipitates, and I'll talk a bit more about those. It will go to cracks and all sorts of places. So there's lots of different places that hydrogen can end up in the structure. We broadly categorize the hydrogen into three categories. The first is the diffusible hydrogen, so that is just hydrogen that can just simply move through the material. So if you charge the steel with hydrogen, then it will gradually diffuse out of the material over time, and that's the diffusible part. What we're particularly interested in are the reversibly trapped hydrogen and the irreversibly trapped hydrogen. So this diagram here is showing you the free energy, and this is the normal lattice site free energy. And if we have a deep trap, as it's called in there, the hydrogen loses energy going into it, and it's quite happy there, and it doesn't want to come back out. And that's called an irreversible trap. So if we can get the hydrogen in there, it's basically out of harm's way. But there are also these reversible traps, which are typically dislocations, grain boundaries, and so on. So the energy does go down, but it's not far enough, and the hydrogen can jump back out of that and cause all sorts of problems, such as hydrogen embrittlement. Now, the theories of hydrogen embrittlement are numerous. People tend to start shouting at each other when they start going through these different theories, because everybody sticks to one theory and it has to be right and the others all have to be wrong, don't they? Of course. But it's not quite like that, actually. But the famous ones are here. The help theory, which basically says dislocations run around, you get pile-up of dislocations, leads to voids, and you get cracking from those. So that is suggesting that the dislocation mobility is much higher. I'll come back to that. HEDI, which is another popular one, simply postulates the hydrogen goes to a cracked tip and it simply breaks the atomic bonds there, changes the bond energy, the cohesive energy there, and the cracks can propagate through. There's one called IED, or whatever you pronounce it, which is similar to HELP, but it's got very important differences you should understand, and more modern theories based on atomistic modelling, which I'll come across again a bit later. So I'm going to run you through some studies that Peng did on what we call the model steel. Of course, there is no such thing as a model steel, but this is high-strength precipitation-hardened automotive steel. So it's interface precipitation, producing very fine titanium carbide or vanadium carbide. And in each case, we modified it slightly with a small amount of molybdenum. But you can see the compositions down here, quite lean, 0.1 carbon, not much else in there apart from the vanadium and titanium. And in each case, 0.5% of molybdenum. So if you look at the precipitate structure within it, then here is the TM image on the left, high resolution. You can see from the scale bar, precipitates really are very fine, typically about 3 nanometers or thereabouts. This is atom probe, showing there's a really high number density, in this case the vanadium carbide, and here's the composition across one of particular carbide, which has got the vanadium carbide, but also molybdenum goes into those precipitates and modifies behavior. One of the few tools that we've got to see where the hydrogen has gone in the lattice is TDA, so it's thermal desorption. So basically we just pump a load of hydrogen into the material, we heat it up over a range of temperatures, and we see how much hydrogen is desorbed at each temperature. The red curve here and the yellow curve are the two steels that I'm going to talk about. So there's a big peak down the bottom, and then there's another peak at higher temperature. The lower peak is associated with trapping in dislocations, grain boundaries, Martensite lath boundaries, and so on. And trying to separate out which of those is important is really quite tricky. In our case, we did it through some atomistic modelling, but there's a lot of debate about that. The higher temperature peak here is the deep traps, the irreversible traps, and those are the ones that are associated with the precipitates. So we can see roughly the difference in material behavior when it's charged. But there's some other very interesting things that happen that are perhaps a bit surprising. TM image on the left when it's uncharged, on the right when it's charged. The first thing that you see is there's an increase in dislocation density in the material. Really rather surprising, but it's not just a small increase. The values here, if you can read them, it goes up by an order of magnitude or so in the dislocation density, just from hydrogen charging. We've not applied any stress or anything like that. Simply from the charging, the dislocation density has gone up a lot. In addition, we modify the precipitate strain field. So on the left here, TM image uncharged. On the right, after charging, you can see the strain field now looks really rather different than it did the sort of classical strain field that we see on the left. This rather enlarged strain field on the right, and that actually leads to an increase in residual strain in the material before you've done anything other than just charge it with hydrogen. I think that's shown again in this image here, high resolution image of the precipitate, uncharged at the top. You can see the precipitates there, you can see the coherent nature of them. When you try and do the same imaging after it's been charged, precipitates here, and you really can't form a decent image within the matrix around it because of this strain. The people at Oxford did some absolutely beautiful atom probe work and charged the material with deuterium in this case. And they were able to show that the in deuterium, and we believe hydrogen as well, actually goes into the precipitates rather than the classical view that it is trapped at the interface between precipitate and matrix. So you can see here the blue is the vanadium, the red dots are deuterium atoms, and they're going through their modeling. They could show here the deuterium was actually located within the precipitate. All the atomistic models suggest it should be the interface between the precipitate and the matrix, but experimentally we see different, so the models are not clearly yet right. Moving on to the mechanical properties of the material, really quite different behavior between the two steels. I mean, they're almost identical steels. They've got the same microstructural scale, they've got the same precipitate type, it's a MC type carbide, same precipitate size, same precipitate number density, but they behave very differently. So here's the titanium moly steel. It's got a higher strength, it's got a pretty decent ductility on the black. As soon as you charge it, it breaks at yield. It completely snaps at that point. It loses all its ductility. On the right, the vanadium moly steel is not quite as strong, not quite as ductile, but when you charge it with hydrogen, it retains some ductility, albeit it is still reduced. Looking at the fracture surfaces, classical, top one uncharged, cup and cone fracture. Lower one here, we can see the cleavage nature of the fracture, classic hydrogen embrittlement. Going up in magnification at that, we can usually work out where the initiation site was. You can see these rather weird features here at the initiation sites, look like holes, and they're often attributed to things like manganese sulfide or some inclusion. But when you do a nice fib section through, so here's this case, we've got what appears to be a hole there, you take a section through it. So this is a cross section along there. This is that hole that you're looking at, which is the initiation site, and then this is the propagation away from that point. You see immediately propagation is predominantly on the 100 cleavage planes, but what we're interested in is what was going on at the initiation to see whether we could see it. It looks a complete mess, very different structure to what we've seen before. So here's that hole that you could see in the SEM. We've got this region around here, the light region, which is very low dislocation density, and then quite an abrupt subgrain boundary that goes around here with a region of very high dislocation density next to it. Really rather odd, we hadn't seen anything like this before. This lovely image on the top right there is precession electron diffraction, so it's showing you the local orientation, different colors, different orientation. You can see these subgrain areas quite distinct and abrupt boundaries with the substrate there. Here's another example just on the other steel, again the same feature, so it's not just a one-off that we saw, multiple sections through these initiation sites. We always see these low dislocation density regions, then an abrupt boundary to a region of high dislocation density. As we go away from the crack initiation site, then you can follow the crack plane, which is here. As I said, it generally goes along the 100 plane, but there's this series of ridges which are associated with where the precipitate lines come up, and they clearly distort the crack propagation direction. Locally, it switches to a 110 cleavage and then switches back again. I think there's beautiful images here, if you can see them, high resolution. Here on the right, the precipitates there are in blue dotted circles. This is the crack path, and you can see it's following really at the atomic scale a 110 cleavage, then it switches to a 100, keeps switching as it avoids the strain field as it goes around those precipitates. Really beautiful image there. And this is a crack tip here. Again, you can see the atomic planes right up to the atomically sharp crack tip there. As say, the dislocation density is much higher at the start, and as you go near the crack, then the charged specimen retains this very much higher dislocation density than in the uncharged state. I'll skip that one. So what about the mechanisms? Does this agree with what all these predictions and so on? So actually this initiation site here with the region of low dislocation density, you can just see a crack in there associated with that boundary with a high dislocation density. So the sequence we think happens here is that hydrogen induces residual stresses within the material, certainly introduces the high dislocation density. But the other thing which I haven't mentioned is the atomic modelling suggests that the mobility of dislocations in steel is much higher in the presence of hydrogen, and that's been confirmed experimentally. So we not only have a higher dislocation density, they are also more mobile. So we think those come together to form these low energy dislocation nanostructures, and that leads to the crack initiation, which you can see here. So it sort of agrees with the HELP mechanism. Some slight differences, we don't get this sort of voiding and that sort of thing taking place, but it is consistent with those observations of crack initiation. But the crack propagation is really quite different. Here we can see the atomically sharp nature of the crack tip, and as it propagates through the material, there is locally no plasticity associated with that, and so this HELP mechanism or the AIDE mechanism, which all involves dislocations going on different planes and forming nanovoids, that does not agree with that at all. It's really quite different. In fact, that agrees better with the HEDE mechanism of just simply cleaving the planes, and but as Curtin has recently pointed out in this paper here, that it's physically impossible for the HEDE mechanism to actually take place because, as he points out, the K1C has got to be reduced to a value well below the dislocation emission, which is physical in itself. So he suggests that that mechanism, as is written down, is not correct. I won't go through his mechanism of propagation, but you can read his paper. It's based on atomistic modelling, and I think it quite neatly shows crack propagation behaviour. So I think what we believe we've got here is a sort of HELP type mechanism in terms of crack initiation, and then much more of a Song and Curtin mechanism in terms of propagation. Right, I hope I haven't taken too long. So to conclude, the carbides are very effective at trapping sites, but we clearly had a very different behavior between the titanium carbide and the vanadium carbide. It would appear that the vanadium carbide gives you an irreversible trap, so the hydrogen is quite safe. But in the case of the titanium carbide, it is a reversible trap, so the hydrogen just comes out under the applied stress and can do much more damage. The charging itself modifies the microstructure, increases high dislocation density, residual strain, and the strain field around precipitates is modified, and also the dislocation mobility. And as I've said, I think this points towards a HELP mechanism for the initiation, and consistent with Curtin et al.'s model of hydrogen induced crack propagation. Okay, that's it. Yep.